Okay, so I guess it's good news that so far we are in a stable kind of situation for the carbon cycle, where it's trying hard to save us from disaster by hiding the carbon we are emitting into land and ocean. By the way, I mentioned several times the unbalanced remaining amount, which is not very small. It's not so easy to hide away order 1 gigaton carbon somewhere, so it's a bit scary that we don't know exactly where it is, even though it's assumed that it's somewhere in the land system. People look for growths of trees hiding more carbon, wetlands, bulbs of some particular plants, and so on and so forth. But remember that some people refer to it as missing sink, some people refer to it as unbalanced amount, but nonetheless we have a good constraint on the emissions, especially fossil fuel emissions, because it's a very valuable commodity and it's kept track of, and we know how much emission comes from there. Land use change, we have a fairly good estimate. There is also cement and so on that is included sometimes, but the sinks, ocean and land, they are difficult to estimate, but all done, there is still some missing amount, right? So for the future, the IPCC projections have typically been using scenarios to make pathways along which we will emit carbon. So there are always something called business as usual scenario. It's called, these are by the way called representative concentration pathways. This is the methodology that was used for the last projection in 2014, and next set of assessments are going to be released either later this year or early next year. They are released every 7 years since 2001 or so, or 97 or so, but anyway, it was due in 2021, but obviously COVID has perturbed the whole system. So there are assumptions about renewable energies, technology evolution, population growth, policy options, carbon capture and sequestration, and so on. And then scenarios are made like this, where the numbers 2.6, 4.5, 6, and 8.5 are the difference in the incoming shortwave radiation and outgoing long-wave radiation. So it's the net radiative imbalance created by the emissions, which corresponds to the greenhouse effect we are creating by additional emissions. So 2.6 means we are going to have by 2100 a net forcing of 2.6 watts per meter squared at the top of the atmosphere. RCP 4.5 is 4.5 watts per meter squared, and business as usual here is RCP 8.5. So that's going to end up emitting, in terms of gigaton carbon, again remember here it's critical because gigaton CO2 is going to be much higher. So we are somewhere here in, let's say, 2021 in the order of 10 gigaton carbon per year, or close to 40 over 40 gigaton CO2 per year, and we're going to be hitting somewhere around 25 to 30 gigaton carbon per year in the business as usual scenario. And these shadings here are uncertainties by the number of models that are used to make these future projections. And there are safer trajectories like 2.6, which you can see that the emission has to start dropping already by 2020, which is gone, so we are not on track at all. By most measures, we are in fact on track of business as usual. This is what is always something to worry about, that despite the huge negotiations talk about increasing electric vehicles, renewable energies, people being conscientious, this, that, and the other thing, our emissions are not budging at all. Okay, and these are the other scenarios in the middle. So obviously getting here is going to be quite a challenge. Corresponding to this emissions in gigaton carbon, you have concentrations that we will reach in the atmosphere. This is going to be close to 1,000 ppm, which we didn't see for many million years in the past. And here is the RCP 2.6, which is going to give us just over 400. We are already at 420, increasing at 4 ppm per year, and so on. So obviously these means the renewable energies have to kick in really soon, and we pretty much cannot do this without having carbon capture and sequestration, which means the future of the carbon cycle is going to be much more of a socio-economic and policy issue rather than a carbon cycle dynamics issue. We are going to basically control the carbon cycle issue. Corresponding to these pathways, 8.6 and 8.5 and 2.6, and the historical warming here, this is where we would be heading. The range of warming with the business as usual is going to be anywhere from above 2 to almost above close to 6, and 2.6 is going to try and keep us below 2 degrees centigrade. Usually it's discussed with a probability of something like 60 or 66%. Okay, 2/3. So here is RCP 2.6, 4.5, 6, and 8.5. So this is what we are looking at in terms of what we will be putting into the atmosphere. So what will happen to the future of carbon cycle? We looked at some of these figures already. So here are the carbon climate feedbacks. So typically people try to do this by saying, what if there was no climate feedbacks, where we would end up, and in these cases, and where we would end up if there were also feedbacks where CO2 increase leads to temperature increase leads to various processes like increased respiration, ocean acidification, coral melting, and so on. So that would in turn feed back to carbon cycle and so on. So that's what this is all about. So business as usual is going to have increasing industrial anthropogenic CO2 flux, atmospheric ocean feedbacks, carbon climate feedbacks. Obviously there is a potential for increased emissions from that in terms of vegetation and agricultural response, wetland response, permafrost response, and so on, and afforestation response as CO2 fertilization, and so on. So carbon neutral situation is where we are going to balance the increased emissions by taking up in the ocean and avoiding additional land feedbacks. You can see the arrow here is bigger. They are equal here. So we are going to keep the system neutral, whereas in negative emissions scenarios we are somehow going to find a way to take out more carbon than we emit. So negative emissions doesn't mean we will be just taking carbon out of the system. It just means that there are unavoidable carbon emissions and we will take out more than we emit, as you can see the red and green arrows here. So these are the kind of potential feedback. So if you have increasing anthropogenic emissions, then you can have negative feedbacks or you can have positive feedback. So the question is, where are we headed? We looked at this before as well in terms of potential feedback. So as climate change and temperature increases happen, atmospheric carbon dioxide is going to create radiative forcing and have a positive feedback. CO2 solubility and ocean carbon pH, calcium carbonate pH stat, etc. are going to drive solubility into the ocean, which is a negative feedback, but carbon uptake is also going to be negative feedback on atmospheric accumulation, but partial pressure is going to increase, so you're going to reduce the uptake by the ocean. So it could be a positive feedback, or you could drive more into the ocean by increasing atmospheric PCO2, fertilization effect here, and carbon uptake effect. So this is going to increase land carbon and decrease atmospheric carbon by carbon uptake. Okay, just heuristic arguments, but what are the things to watch out for? Okay, the big iffies are what we talked about in the Paleocene Eocene thermal maximum in terms of methane hydrates. So methane hydrates occur in all of the oceans as well as on land. So these are different methods here. Green dots show occurrences in the northern permafrost regions here. A big reservoir that shouldn't be perturbed too much. Occurrences identified by Geophysical methods are in red. The occurrences shown by blue dots were verified by direct sampling. So basically all these are susceptible to global warming and human perturbations, especially because they are in coastal regions. Coastal populations and coastal activities continue to increase, and warming of the ocean in the coastal regions also potentially make them unstable. But this is a large uncertainty in terms of what we are doing. For example, there is what is called polar amplification or Arctic amplification, where the warming is much larger in these regions because of cloud feedbacks, water vapor feedbacks, ice albedo feedbacks, and so on. So how vulnerable are these permafrosts and other storages on land and in the ocean? Always worrisome, because that would be a very rapid feedback to the system. And permafrost, I think you know what that is. These are basically frozen soils which have buried organic carbon and methane. Seasonally, the permafrost thaws at the top down to some depth and then refreezes during fall-winter months. But the freezing depth is increasing with surface warming and the Arctic amplification, and they have various levels. So this is carbon in the top 3 meters of the soil in kilograms per square meter of surface area. You can see there are some high carbon areas and lower carbon areas, and with Arctic amplification and sea ice melt and the craziness, is there potential for release and positive amplification of the overall carbon cycle feedback? So will the carbon cycle go completely unstable in the coming decades and out to 2100? This is a key question that must be understood much better. I will stop this here, relatively longish already, but we will talk a little bit about what we are expecting in terms of how long the system may take to equilibrate. We talked about the long time scales with weathering CO2 thermostat and the unstable ice age feedbacks, which we didn't completely answer which feedback would have worked to explain the positive feedback, which is an concern for where we are headed, because we don't completely understand how the CO2 and temperature positive feedbacks work, which concept, increased solubility, pH, circulation changes, or biological pump is going to help us or not. So that has to be left open at this point as models try to understand better and better as to what the carbon cycle will do, but of course uncertainties remain large.